Okay, here we are in POE talking about vectors. Am I coming through the mic? Yes? Okay. I'm not hearing it as well, but... All right, so let me hide this. All right, so first of all, vectors have a magnitude and direction. And there's different ways in looking at vectors and how we do things in physics or engineering class or in math class. They're sometimes noted a little bit differently. So the magnitude in some textbooks, you'll see looks like a single absolute value. That means magnitude. A vector can be written just, vector A, vector B, instead of, with looks like a ray symbol over it, but that's a vector. Or that magnitude can be written as the force of vector A. So see, that's another way it's written. Not a big deal. This is just different notations. All three of those mean the same thing. Okay? We okay with that? When we're looking at vectors in math class, they write vectors sometimes with an I plus j form, and where the I is the x value and the j is the y value. And the only reason they did that goes back to 100 years ago. They started typing things out, and they didn't have a good way to type mathematical symbols on a typewriter. So therefore, the mathematicians, to make things easy, said, oh, let's represent it with an ij as scalar quantities. Of course, then you can turn any xy component into a right triangle, and you got Pythagorean theorem to find the magnitude of the vector. Okay? Does that make sense, guys? That's theta. Greek letter theta is often used, right? Greek letter theta, let me get my marker. That's a very sloppy theta. But Greek letter theta is often used to represent an angle. Okay? All right, can I move on to this slide yet? Yes? Okay. And some of the other slides that are in the actual PowerPoint, I've got combined on one page, which makes taking notes a little bit easier. So with the magnitude, here's an example. It has a magnitude of 3 units. That would be pretty simple. And we can say it's 30 degrees. So it's going to have a magnitude, direction, and a sense. Okay? What is the sense? Of course, the direction, we always go to the x-axis with angles. So there I have another vector drawn. The 54-degree angle will be the angle that's important. Reference angles always go to the x-axis. So if you have a diagram and they give you a y-axis vector, all you got to do is subtract from 90, right? If you start doing a problem with the wrong angle, you'll get all incorrect answers. Okay? So that's pretty simple. In math class, you're just starting your triangle trig. We also do angles of rotation. I don't know if they still teach that in geometry or not until Algebra 2, where you look at pre-calc. Did you do that in geometry or not until Algebra 2? You're not sure. Huh? Pre-calc students? You're not sure? That's not really picking up all that much. So really, if you're, little trig review, okay, if I have an angle, positive angles start rotating in a counterclockwise direction because they rotate through the quadrants. Julia, do you remember? You're in Greek calc. I don't remember if it was done in geometry or algebra 2. Angles of rotation. They're just starting on triangle trig, so they wouldn't have done angles of rotation yet. So I don't know. So like, you know, a positive 200 and, you know, where are we at here? Let's say positive 210 degrees. That would be, would rotate down here and we would have a 30-degree reference angle. Okay, does that make sense? If it's a negative angle, it rotates clockwise. Well, that's your starting point for an angle of rotation in math class. In engineering class, when you're talking about cams, 0 is vertical with the autometer. You know, so again, sometimes the rules change. As long as everybody knows how they change, it's fine. You just take it and turn it 90 degrees so that 0 degrees is vertical when you're looking at a cam. So we did a little bit of angles of rotation with automatons last year. You just didn't realize a whole lot with it, right? So, all right, let's. The sense is basically just the direction. Is it going up and to the right, up and to the left, down and to the right, down and to the left? Which quadrant are you ending up in? Sense is just a very generic description. Where is it going? Okay? I don't think we need a lot of notes on that, right? Just basically describe where is it. All right, right triangle review. Okay? So, of course, pretty basic. You got to know your, what? Angle sum theorem, 180 degrees for your angles, Pythagorean theorem. We have the hypotenuse, the adjacent side, the opposite side. All right? Are we comfortable with this? Some of us are just now doing trig for the first time in geometry. So it does overlap. That's also one of the reasons that even in a normal year that's not a pandemic, we're a couple months behind. But I usually do some robotics in November. And we were almost going to get there, and then we realized, no, we didn't have time, so we did something else. Right? Oh, and then we went virtual. Yeah, virtual robotics would not be. Huh? Yeah. Let's see. So, all of that should feel comfortable for you, right? Again, if we're advanced math students, those are pretty basic. And if we're in geometry, that's something we've just gotten into. And then, of course, what is our application? So, now, what we do in geometry class, we always label things. You know, we have our SOHCAHTOA, and SOHCAHTOA is on your formula sheet. Okay? But so we have, you know, our opposite side, adjacent side. When you start applying this to vectors, okay, SOHCAHTOA is like 5% of the problem, of solving a problem. And the problems get rather intense. If we get into a truss calculation, I can pull out an engineer's notebook from a past student. When you get into a truss calculation, let me see if I can find one of these. Oh, wrong one. Okay, just so you get a sense of where we're headed. Okay, and I'll probably leave this out again. There's one problem. Okay, and she left some space. Could you cram that all on one page? Probably. If you write big, you definitely take 2 pages. That's one problem. Okay, so solving the right triangle trigonometry is like 5% of this. Okay, so this is again, something that my college students say they wish we did more of, but you're gonna be glad that we do. About, you'll be comfortable. Some of you will be comfortable with it by the end. Some of you will still be like, I kind of understand what's going on, but there's a lot going on and a lot of little steps. It's okay. Okay? So, for that reason, because we're looking at a vector, okay, what we try to do is, instead of just thinking of opposite and adjacent sides, we're going to kind of simplify this process, because if this is our angle, the vector has an x component and a y component. It's pulling to the right, and this vector is pulling up. So it's going to the right and it's going up. So the opposite side, we, in physics class and engineering class, we label as the force of the vector A in the y direction, F-A-Y. Okay? What do we have? The adjacent side we label as F-A-X. It's the force of vector A in the x direction. So what that allows us to do, okay, is if I take this relationship and rewrite it, instead of just opposite over hypotenuse, it's force of AY over force of A, okay, then if I solve, because a lot of times we have to break these down into the component vectors, let's see, if I take that proportion, sine of theta equals F-A-Y over the force of A, okay, if I set that up and make it a proportion, if I want to isolate F-A-Y, the force of A in the y direction is the force of A times the sine of the angle. Okay? That solves it, and you know, in engineering, a lot of times we solve it with the variables first, and then plug in our numbers. There's so many numbers to plug in and write down, it makes it simpler, right? Instead of plugging in numbers and then trying to solve. So if we extend that to all these other ones, we can do that with all of them. The force of A in the y, force of A in the x direction would be the force of A times the cosine of the angle. So, simplifying to this point with those two simplifies the entire problem for us, because now we're breaking it down into those two components, and we don't have to draw the right triangle. The x component should always, the x component is always the cosine. The y component always uses the sine function, as long as we use the reference angle to the x-axis. So that's why, you know, and I guess I don't have the force of A in the y direction, force of A in the x direction. So that's where this is a shortcut that is going to make the next 2 weeks a lot easier. Okay? Everybody with me at this point? Mostly? Okay? If we have multiple vectors, okay, what is this? What Greek letter is this? What does that mean? That's Greek letter sigma, capital sigma. Lowercase sigma, remember, is this one. Well, that's lowercase sigma, which is standard deviation. If you're in Algebra 2, you'll be doing a little bit of standard deviation and t-values and statistics coming in at the end of the year here. Here in pre-calc, I'm not sure what you covered last year. You might have missed some of that because of pandemic, I don't know. But if you have multiple vectors, you take the sum of the vectors. This is just the sum of all the different vectors in the y direction. This would be the sum of all the forces in the x direction if you have multiple vectors. Okay, I think that's the last page of notes, and then we have some examples that we'll do, and then some practice problems. And looks like we might get through one example today, and then yeah, like I said, 3 days, especially with the fire drill and wrapping up talking about bridge competition. Okay? So I think the next slide is an example. Yep. All right, so what do we have here? We have this vector, right? Has a magnitude of 75 pounds of force, pulling down and to the right. So sketch that vector real quick. So we said it's 35 degrees clockwise from the x-axis. That's it's going down and to the right. Okay? Maybe we'll get through 2 examples, but maybe we'll see. We'll see where we're at. Yeah, one of my former students was complaining. Well, she had a breakdown and emailed me at like 2 o'clock in the morning, I think her sophomore year, and said she had got through about 2 hours of crying because she was in statics 2 and dynamics, and probably physics 2 or 3 or something like that. But she was just like, okay, she was having her come to Jesus moment of, I'm either going to get through engineering, or this is the moment where I say I'm going to do this and I can do it, or I'm going to change my major. A lot of people have that moment, and you know, and now she's got her master's degree. She's working in Colorado. She got hired 6 months before she got her master's in civil engineering. So, you know, and it was this, what we're doing now, led to that, but it's tough stuff. Baby steps here. So, solve for f of bx. So the force of b in the x direction. Well, if we use the shortcuts, that's really easy, right? What's the shortcut? Shortcut, though, is not on your formula sheet. The force of b in the x direction is what? What's the formula? We just copied it down. Julia? Yeah, it'd be the force of b times the cosine of the angle. So we can write our formula down. And the force of b is 75 pounds times the cosine of 35. Now, of course, one important thing you have to do is what? With your calculator. No, well, yeah, but make sure you're in degrees. The default on a calculator is radians. Okay, and in pre-calculus, you start going back and forth between radians a lot. Not mode. You got to go into mode on your calculator. So somewhere in mode, you've got degrees and radians, and if you're not in the right mode, we have a problem. You want to be in degrees. Huh? You're in degrees already. Yeah, if you're in, once you change it, it usually changes the settings, but from the factory, it starts in radians. Okay? So 75 cosine of 35, what do we get? 61.44. And solve for the force of B in the y direction. So the force of B in the y direction is the force of B times what? Sine. The sine of the angle. So in this case, that's going to be 75 times sine of 35 to the end. 43.02. Okay. Now, as a double check, you could do Pythagorean theorem and make sure it comes out to about 75. I guess we probably could have rounded at one significant figure. I don't get excited about significant figures. Science teachers do. In engineering, the precision we need, the precision is different with engineering. It depends on how precise we need to be with a mechanical drawing or whatever. So, how much time is left? Enough time to copy down the next problem, right? But that's probably it. Okay, that's all we got. Is that hard? No. Could you do SOHCAHTOA if you forget the shortcut? Yes. Huh? SOHCAHTOA is on your formula sheet. Okay, so you could do SOHCAHTOA if you forget the shortcut. When you get into an advanced problem, the shortcut, just always know the shortcut makes it simple. All right. So just copy the problem, and we'll start off with that example tomorrow, and then that should get us plenty well into the first assignment. And then Friday will be a second assignment with a few more practice problems. Yes, Sean? Oh, Sean has called us on this. Thank you, Sean. What do we got to do on this? We forgot something. Okay, and I should have pointed this out, but the y force is negative. It's going down. That negative is really important. If we were in a truss calculation and we have the wrong sign, we got a problem. Right? Where are we going? It's 61 to the right. That's positive. 43 down. That's negative. Okay, that's important. Good call, Sean. I think that deserves a Laffy Taffy. Got to read the joke. They're all bad, but we all get to grind together. All right, so let's stop the recording.